Okay, we're all here. Finally. We've made it to the end of the semester almost. Just one stinking test left. And it's not a final. Remember, it's just a midterm. It's just on this wave section, this last two chapters here. So what questions do you have tonight? What's got you worried?
This is the first one. So, this is those. Why is that?
Yes.
Can you go over how to find maximum acceleration and some.
I'm sorry?
Maximum acceleration.
Oh, yes, maximum acceleration. When you hear acceleration, I hope that your mind goes back, to the before times, the second part of the class on dynamics and Newton's second law, which is, as we promised, the most useful law of all the ones we learned this semester. And so if you're asked for the maximum acceleration, it's for a given mass, it's going to be when I have the maximum force. And these types of problems are typically dealing with a mass on a spring. Now, with a mass on a spring, there's an equilibrium position. We typically call that x0. And that's the length of the spring that it came from the factory, that long. When you took it out of the box, it was that long. And so if you connect it to that mass and you set that mass there, it's going to stay there forever. It's not being pushed at all. If I pull that out some distance a, we call that the amplitude, then it'll go back and forth. Okay, goes there, back and forth, back and forth, back and forth. Now, the force in this case, if I do a free body diagram, let's say I do it when it's here, I have weight down on the block. I've got the normal by the table up on the block, and they cancel each other out. There's no acceleration up or down. The only unbalanced force that goes into here is the force by the spring. And that's given by Hooke's law, where that delta S is how far it is away from this equilibrium length, okay? But when I get to the turnaround point, my delta S, we just gave it a name, call it a Bill, a Mary, we just call that the amplitude. But it just happens to be the biggest value that we get for delta S, the turnaround point. And because that's the biggest value for delta S, it's also the biggest value for the spring force, which means it's the biggest value for the net force, which is going to yield me the biggest value for the acceleration. Does that answer your question? Okay. Yes, sir.
In that same kind of problem, how would you calculate the amplitude? I guess if you have the energy, how do you know what the amplitude is?
You answered your own question and in a profound way. If I have the energy, then you remember there's two buckets involved in this type of problem. For the total energy, I've got the kinetic energy in the motion of the block, and I also have the potential energy stored in that spring that's stretched or compressed. Now, in order to turn around, I've got to stop. I got to stop to go the other way. And that location, like I said, we call the amplitude. And so if I know that total energy, I look at the turnaround point where none of the energy is in the motion bucket, and it's all going to be 1/2 k delta S squared. But delta S has a special value at that location. It's the amplitude. Okay, and so that's what you have to look for first, even if there's no points in it. Even if you haven't been offered any points for finding that energy, if you've got one of these block on a spring problems, that's what you go for first. What is the energy in the system? Because that's how we solve it. Because that table is frictionless, I don't lose that energy. And anything that stays constant, I can work with that. You know, if I know that it always stays 9, I can work with that. You got a question?
Say in that circumstance, then you would probably give us the amplitude, right? We wouldn't have to like figure out 17 variables.
Well, there's all sorts of ways to play this. I would probably give you the mass of the block, but I could say there's a homework problem where the amplitude was 16 centimeters or 0.16 meters. We always put it in meters when we do these things, okay? And they said, well, what if it wasn't a turnaround? And what if it wasn't at the equilibrium point? What if it was right here, you know, at x equals 12 centimeters? Well, in that case, I couldn't use this formula, but I can always use this formula. And so if I were to tell you how fast it was going when it was 12 centimeters away, and you knew the mass and the K, you could calculate the energy. And then once you had that energy, you could predict what the amplitude was going to be. Or if I look at equilibrium, the delta S is 0. There's no energy in the spring. And that means that all of the energy is in the kinetic energy bucket. And that's where it's going the fastest. So I could say, well, that same E total is now equal to 1/2 mv max squared plus 0. Okay, so this would be at the turnaround point. And this would be at equilibrium. But this always works. You know, if you only have one equation you want to remember that one. And sometimes you plug in 0 here and sometimes you plug in 0 there and you get the other two equations. Okay.
On the practice exam that you gave us, there was this equation. T equals 2 pi square root mass.
Yes. That equation you have to be careful with T. Okay. The English language just has so many letters, and so we end up overusing some of them. And so when we're dealing with the speed of a pulse on a transverse pulse on a string or a spring or a rope, that was equal to T over mu, where this was tension. That's a force in newtons. But here, that T stands for the period. And in this case, T stands for time, the time it takes to make one oscillation. And so this is either a mass going up and down or a mass going left and right, doesn't matter. As long as it's a mass on a spring, you can plug in the mass and you can plug in the spring constant, and that will give you your period. Now, where does that formula come from, Greg? Well, it comes from some ugly mathematics, a differential equation that we just couldn't do, given the prereqs for this class. And so this is one of the times, and I feel, a little dirty doing it, but it's one of those, trust me, you really don't want me to go there to derive that equation, but it turns out to be true, and you can, I gotta tell you, a lot of middle school science projects have been put together at the last minute with that equation right there. You put a mass on a spring and you show people that, it doesn't depend on the amplitude, it doesn't depend on the speed that you started with, it just depends on the mass and the spring constant. And it's a nice simple, when your parents and when your kid tells you at probably 10:30 at night, I got a science fair project due tomorrow, go to that equation right there. Okay. Find yourself a spring somewhere in the class, in the house. Okay. The other thing to remember when using this formula is that square root. Okay. If I want to, and the formula, we can't derive it, but we can see that it makes sense. The bigger my mass, the more inertia I have, the harder it is to get it to speed up and slow down. That's going to slow down the motion and increase the period. Likewise, if I have a really strong spring, you've seen strong springs and they have that big restoring force that just, the mass tries to get away and it yanks it right back. So that's going to make the period smaller. But because of this square root here, in order to double the period, I'm going to have to quadruple the mass. Now, this is the formula, but it's not the most useful form of the formula because of that square root. And so I like to square both sides. So to get rid of that square root. And then I like to cross multiply here. Oops, notice I forgot something there. So this is how I would find a spring constant. If I were told, say in an exam, say it's a final exam, I put a 4-kilogram block on a mass and I found that it bounced up and down with a period of 2 seconds. What's the spring constant? You just plug into that formula and you've got it. Now, that's one way to find K. We call that the dynamic method. There's another way that we call the static method. And that is you just take your spring and you hang a mass on it. Static means not moving, and so you just hang it there. And what you want to do is measure how much that stretches the spring. and then use Hooke's law. And so if I know that this is a 4 kilogram block, then I've got a weight force that's 40 newtons. And the other force there is the force by the spring. So I can plug in 40 newtons, and let's say this delta S is 0.1 meters. And that gives me a K of 400 newtons per meter. So that's the static method. And my feeling is you'd probably be asked to find K both ways on the exam. Okay.
I would notice like as I was going through the homework and like the practice exams that sometimes it would say like wavelength is like half of the length or like wavelength is like 3/4 of the length. Is there like an easier way to like I guess tell like what the relationship is between wavelength and length?
Uh, the wavelength and length of what?
I guess of like the length of like a cylinder versus like the
Oh, yes. There are two formulas that are more valuable than all the others in this part of the class. The one is the wave equation, because it works for all waves, standing, traveling, longitudinal, transverse, every single one. And then there's this formula, number of footballs times lambda over 2 is equal to L. Okay. And you'll never see that formula in any other class, and it's only because I'm an old man with no shame that I'm not afraid to put it up on the board. But if we remember that it takes 2 footballs to make a wavelength. And so if I just count the number of footballs that I have, and remember that each football is half a wavelength, that's going to tell me how long my system is.
So when I was looking at sample exam number 1, on that first question, it uses this equation, but it has 4 in the denominator instead of 2. Why is that? It's when we have to figure out how long the pipe is in 1C. And you have to use that equation right there, but instead in the key it has 4 in the denominator instead of 2.
Are you looking at that right there?
Yeah.
Okay. How long is the pipe? Well,
Can we actually just go through this problem? That would be great.
oh, sure. Okay. Let's look at that problem. That's a very important problem. Or need some WD-40. So if I have let's say I have a pipe that is open at both ends, then I have to have an antinode at both ends. And I can't just go from an antinode to an antinode. That's just wind. So I have to have a node in between. And so it's going to look like that. Okay. And in that case, I've got half a football, half a football. And so when I use that football. I would have one football times lambda over 2 is equal to the length of this pipe. Okay. Now, if that fundamental frequency was, say, 100 hertz, then I know that I could also find resonance at 200 hertz, 300 hertz, 400 hertz, 500 hertz, and so forth. Now, if that pipe were closed at one end, then this has to be a node, and this is going to be an antinode, and the longest wave that's going to fit is going to look like that. Okay. Now that's only half a football. And so if I go a half football times lambda over 2, and that's going to be L, well, that's where I get L is equal to 1/4 of lambda, or as it is in that solution there, lambda over 4. That's where I get that. And if this, and you'll notice that I drew this length half as big because I wanted the same size footballs. If the footballs are the same size, then the wavelengths are the same size. If I go to the grand high equation, if I'm dealing with an organ pipe, this is 343 meters per second. It's a constant. And so if this stays the same, then so does this. Okay, and so if I've got the same size footballs, this F1 is going to be 100 hertz. But now I'm not going to get 200 hertz out of this thing. All the even harmonics are gone, we found. Okay, and so I'm going to get F3, which is 300 hertz. I'm going to get F5, which is 500 hertz. And I'm going to get F7, which is 700 hertz. Now, the reason for that is that every time I go to the next allowed resonance, the next allowed booming sound, I have to add a whole football. And if I add a whole football to this, well, I double the number of footballs. I go from 1 to 2. But if I add a whole football to this, I triple the number of footballs. I go from a half to 3 halves. Okay, and if I add another football after that, I go from 3 halves to 5 halves. That's why all of the even harmonics are missing. If I go back to this equation here, if I'm cramming 3 times as many footballs into the same space, my wavelength is getting 1/3 as big, which means my frequency has to get 3 times bigger to make this equal the same. So back to your question, how do we solve these problems where I'm told, oh, it resonates at 400, 560, and 720? Well, use a different color. Okay, it resonates at 400, 560, and 720. Well, you notice that with whether it's open, or open, closed, there's always the same spacing between resonances. Now down here it would be 200 hertz. 200 hertz. So I know that if I know these 3 resonances, I can find all the others. Okay, I just look at how far they are apart. They're separated by 160 hertz. 160 hertz. So I just march my way down, getting lower and lower, looking for the fundamental frequency. So if I subtract 160 off of 400, well, that's going to give me 240. And if I subtract another 160, well, that's going to give me 80. And if I subtract another 160, I get a negative number. And you can't have a negative frequency. So the rule is you march yourself down and you don't go negative and you don't go to zero. Okay? You go to the lowest number that's not zero and not negative. And that lowest number is going to be F1. Now, here's the most important step. You have to look at this next to the lowest and ask yourself, is that F2 or is that F3? Well, if it were F2, it'd be 2 times 80, which is 160, and it's not. 240 is 3 times 80. So this is F3, this is F5, this is F7, this is F9. So immediately, I know that this is an open closed pipe because all the evens are missing. Now, let's look at this here. I chose to use the fundamental wavelength to find the length of that pipe. But I could have chosen this fifth one. Let's do the fifth one just for kicks and giggles, okay? So for the fifth harmonic, I have 5 halves footballs times lambda over 2 is equal to the length of the pipe. And that tells me that the length of the pipe is going to be equal to 4/5 times lambda 5. Now, wait a minute, Greg. You said the length of the pipe was 1/4 lambda. Well, that's lambda 1. That's the longest wavelength of the fundamental. I'm doing it now for the fifth harmonic. And to find that lambda 5, remember this equation works for all the harmonics. It works for one, but it also works for 5. Now, folks, I'm an old man. I've seen a lot, but I keep seeing the same lot over and over again, semester after semester after semester. And that is, I see people plug in frequency 5 and wavelength 1, or frequency 1 and wavelength 5. Garbage. You get garbage, okay? These have to be the same. So I know that this is 343 meters per second. I know that the fifth harmonic, well, the fifth harmonic is 400 hertz. And now I can solve for lambda 5. I can plug that in here. I'm going to get exactly the same number for my answer, 1.07 meters. Okay. So it doesn't matter which harmonic you use as long as you stay consistent. Now, you saw how I got the fourth there is because I had a half football times lambda over 2. And that plus that gives me the fourth.
you go over on the last homework problem too, that talks about like
The last homework problem,
number 2 on the last homework.
oh. Certainly. And these homework problems, most of them, nearly all of them, are old exam questions. Oh, you're talking about this one here?
Yeah.
Oh, good. I love that one. Okay, so. So we have this pipe. And which harmonic do we have resonating in there? The second harmonic, yes. And so I have two nodes. So I've got an antinode at the ends, and I've got an antinode in the middle, a node in between all the antinodes. And so what this looks like now, I hope that you got the message that this football representation is really, really good for transverse standing waves, where it actually looks like a football, and really, really poor for these longitudinal standing waves, where nothing looks like a football. The football representation, all it's good for, all it does is tell me where the antinodes are and where the nodes are. That's it, okay? But the particles are moving along the pipe like this, back and forth. And here's the thing. If I know how one particle is moving, let's say that one right there, if I know that when we took the picture, it's moving to the right, I know how all the other particles are moving, okay? Now, it's important to think of this in terms of slices of air, okay? The node isn't right there. The node is this whole slice of air particles. None of those particles are moving. They're being crunched from both sides, and then they're being deserted from both sides, and then they're being crunched from both sides, then deserted from both sides. It's this sloshing that goes on that causes the sound that you hear, okay? And so this particle is not moving. This particle is not moving. This particle's not moving. This particle's not moving. This particle's not moving. Now, likewise, I can think of this antinode as a whole slice of air. And so if this particle's moving big to the right, so's that one, so's that one. Now, here's the other piece. All of the particles in one football are moving the same direction, okay? So if these guys are moving to the right and they're part of this football, if I look at a slice right over here, they're moving to the right. But they're not the antinode, so they're not moving as far to the right. Now, the fact that all of these are moving to the right tells me that this node is in the process of being deserted, and it's deserted from both sides. And in the antinode, it's got the biggest motion. Now that means that this slice of air, the other node, it's being crunched. And that's always going to be the case. When one node is being deserted, its neighbor is being crunched, and it's being crunched from both sides. And the antinode has the biggest displacement, okay? Now, That's what all the motion looks like when I took the picture. If I waited 1/2 period later, all of these would be reversed. And now this node would be crunched and this one would be deserted. Just back and forth, back and forth. Okay. What I tell people is, go in your bathroom, lock the door, fill up your tub, get in and start scooching. Okay. And if you get scooching just the right, you're going to get a slosh in the middle of the tub. That's a fundamental. Okay. Scooch twice as fast and you're going to get the second harmonic and a lot of water on the floor. Okay. Remember to lock the door. Okay. But it's the sloshing that makes the sound. Without the sloshing, you get no sound.
Do a mock cone problem.
I'm sorry.
We do a mock cone problem.
Oh, certainly. Mock cone problem. There's two ways to dance those. I can either give you all the geometry and ask you for the speed of the plane, or I can give you the speed of the plane and ask you something about the geometry. So let's look at both cases. So we'll say I've got a plane that is traveling at Mach 1.3. Okay. And that's going to give me a Mach cone. And if I tell you how high the plane is, I can ask you how far it gets down the road before you hear the baboom. If I tell you how far it gets down the road before you hear the baboom, I can ask you how high it goes. And the key is to first of all find this angle through the use of this formula here. Okay, so that angle is going to be the inverse sine of 1 over 1.3. So you take your calculator and you plug in 1.3, you hit 1 over, and then you hit inverse sine. 50 degrees, okay? So this is going to be 50 degrees. And now I know that the tangent of 50 degrees is equal to the opposite side over the adjacent side. So if I give you h, you can find x. If I give you x, you can find h. Okay? Now, the other way to dance this is that this thing's got a Mach cone. And I tell you, h is equal to 1 kilometer. I hear the sonic boom after it travels 1.7 kilometers down the road. How fast is it going? Okay. So in that case, I just dance this one backwards. I first of all find the theta, but this time I find the theta from the geometry, not from the Mach cone formula. And so I say the tangent of theta is equal to the opposite over the adjacent. And that means that theta is equal to the inverse tangent of 1 over 1.7. So again, I go back to my calculator. I say 1.7, 1 over that, and then I go inverse tangent, 30 degrees. So this is going to be 30 degrees. Now I use my Mach cone formula. The sine of 30 degrees is equal to 1 over the Mach number. Well, the sine of 30 degrees is 1/2. That's equal to 1 over the Mach number. Well, that means the plane is going Mach 2, or twice the speed of sound.
So does that mean that the Mach number is your hypotenuse?
No. No, the Mach number is not the hypotenuse. No.
So then why could you do for tangent of theta 1 over 1.7? Is technically.
That changes everything, doesn't it? This 1 stays 1. This h just happened to be 1 in my example.
Okay.
Okay. So the Mach number has nothing to do with the hypotenuse. Absolutely nothing. Uh-huh.
There's a question in the book just like it. Could we go through it?
No, absolutely not. That problem makes me mad. That problem causes me to lose sleep at night. Ron Hellings was one of my best friends. I dressed his body at his funeral. I sang at his funeral. I love the man. But that problem is wrong. And I told him it was wrong. And he argued and argued and argued. And he went to the other side, believing that is wrong. But he knows now. He knows now. Okay. Yeah. Yeah. And
Did the math and I did how I thought I did it right, and then I double checked it with ChatGPT, our dear friend, and even Chat got the same answer as me, and then I looked in the back of the book and it was something completely different.
correct.
So I
And
was really
and if you look at the solutions that we've posted online, there's a correct answer, not the one that's in the back of the book. So
just wanted to make sure that
there are errors in the book. The publisher has an interesting philosophy, and that is that, they wanted to make the book and never make it again. Now, my other textbook for the conceptual physics class, they wanted to rewrite the book every 3 years. And so I was on this treadmill. Every 3 years, I had to rewrite the book, do all the new problems, everything, because they wanted to sell books. They wanted everyone to have to get a new book every 3 years. It was a racket. But this publisher that was Universal Science Books and then became AIPP, and today I got a letter saying they just sold out to MIT Press, so that's the new publisher. They just wanted to publish it once and never again. And so the mistakes that are in the first edition are still there because we don't get a chance to rewrite it every 3 years. And so the best I can do is just warn you that there's problems. Sorry for that rant, but it causes me to twitch. Yeah. Yeah.
It's down.
What I ought to do is just offer 50 extra points for every mistake you can find in the book, and then people would read the book. Yeah.
There is this question, a periodic wave is produced by on a stretched string, which of the following is not related to the or to the speed of the wave?
Yes.
And the correct answer was amplitude.
So
Thanks.
so that it's on a stretched string means it's a transverse wave, and I know that for a transverse wave, I have this formula for speed. Where mu is the mass density, linear mass density. For a longitudinal pulse or wave, we're talking a sound wave, and it's 343 meters per second, full stop. Okay. Now, these are not the only formulas, because we also have the grand high wave equation, which gives me the velocity. And so there's more than one way to get at a velocity. And so if I look at that question, it's not that one. A periodic wave, whoops, all the way down here. A periodic wave is produced on a stretched spring. Which of the following is not related to the speed? Well, the frequency is something I can use to find the speed. So that's out. The period, well, the period is 1 over the frequency, right? So that's out. The wavelength, well, that's here. So that's out. The tension in the string, that's here. So that's out. What's left, my dear Watson, must be the truth. And the amplitude just never matters. Okay, that's the simple in simple harmonic motion. It's the amplitude never matters. Okay. And that's a blessing, because the mathematics of physics would be so much more complicated if simple harmonic motion depended on the amplitudes. But it doesn't. Yeah. This class could be a graduate level class if it weren't for that little piece of tender mercy, I call it. It's a tender mercy.
Okay, there's this question is like, it's pretty long, and it's the first one on the second practice exam. It's the one that like they're on the cart and they're going down the hill and then they hit the screen.
Okay.
If it's too long, then that's okay, but I was really Yeah, I think it's that one, yes.
Okay. So let's look at that. The first part asks us to go back a little ways to the energy part of the class and use the fact that if this is a frictionless track, that the energy initial, which we'll call point A, plus Verk is equal to energy final. We'll call that right here. And since it's a frictionless track, there's no Verk. Now the initial energy, I ask what kinds of energy do I have? It starts from rest, so it's all going to be gravitational energy. And when it gets down here, if I call this my height 0, it's all going to be kinetic energy. And we see that in both cases, I've got the mass there, so it really doesn't matter what the mass of the cart is. And so, well, it does, because I'm not asked for the speed, I'm asked for the kinetic energy of the cart. So if I take the mass of 400 kilograms and multiply it by G, which is 10 newtons for each kilogram, and then I multiply that by 50 meters, what I get is 20,000 joules. Okay. I hope I did that right. 200,000. Okay. It's a big number. 200,000 joules. Okay. Now again, once I know the energy, that stays constant as this thing bounces back and forth. And so I can say that that total energy is equal to 1/2 mv squared plus 1/2 k delta s squared. That's the general. But I know that at the turnaround point, I've got to stop to turn around. So this goes to 0, and this goes to 1/2 k a squared. So I plug in 200,000 joules is equal to 1/2. We're told that the K is 1,000 newtons per meter. And now I just solve for A, and I get an A equals 20 meters. So far, so good. It's a lot of just algebra, okay? Now, if I go back to this general equation, I have all sorts of power, okay? If I know that this is 200,000, you tell me how fast it's going and I'll tell you how far it is from equilibrium. Or if you tell me how far it is from equilibrium, I'll tell you how fast it's going. There's all sorts of things I can ask here, okay? And so in this case, I'm told, what if I'm 6 meters from equilibrium? If I were 20 meters from equilibrium, I'd be stopped. That's a turnaround point. But I'm not. I'm only 6 meters away. So I would say 200,000 joules is equal to 1/2 times 400 kilograms times v squared plus 1/2 times 1,000 newtons per meter times 6 meters squared. And then I just solve for V. Now, here's the sad news, is that the biggest mistake made with this problem was not in their understanding of the physics. It's not in their understanding of algebra. It was their failure to do the square. They forgot that square there. They even wrote it down, they just didn't do it when they were calculating things. Now, if this were an exam like I was giving in Montana, where I had graders all night long grading, the long answer, we would put an X there and say, oh, you forgot to square it, and would take a point. But this is a multiple choice question. And so if you don't have that square there, you got the wrong answer, you lose all the points. Okay, that's sad, but it's life. Okay, so if I do this algebra, what I find is that it's going 30.2 meters per second. Now, the maximum acceleration, remember, we talked about that right at the beginning. That happens when the force is maximum, and that happens at the turnaround points. And so I would say F max is equal to Ka. Well, let me do that in steps. F max is equal to K delta S max, but I have a special name for delta S max. That's the amplitude, okay? So that's going to be 1,000 newtons per each meter times 20 meters, and that's going to equal 20,000 newtons. And now if I just use F net equals MA, 20,000 newtons is equal to 400 kilograms times A max. And I get my maximum acceleration. Now, this last part is where a lot of my students had the most trouble. The rider gets tired of this oscillation because there's no friction. It just goes back and forth, back and forth. They're not nearly as tired as the people that are waiting in line to get on the ride. They're never going to get on the ride. So these guys do the ejection seat straight up into the air. If it ejects right at a turnaround point, what's going to happen to the motion of the cart? Well, right at the turnaround point, if I look at that formula for the energy, if I look at the turnaround point, all of the energy is in the spring. None of it's in the motion of the cart. So it doesn't matter how much mass we have involved. It's just how strong is the spring and how stretched is the spring. So I still have 200,000 joules in this system. I just don't have the riders, okay? But I still have the same maximum energy. Well, that's going to have some consequences when I get back to my equilibrium position. Because now, at equilibrium, all of the 200,000 joules is in the motion. And if the mass got smaller, the speed has to get bigger. So it's going faster in the middle. So the amplitude's got to stay the same. Because when I get, when the 200,000 joules is all in the spring, that amplitude stays the same. The period of the speed of the cart at equilibrium will increase because this is still 200,000 and the mass got smaller, the speed got bigger. The period, remember we had that formula that we couldn't derive, but we took Greg's word for it. The spring stays the same, but the mass got smaller. So the period gets smaller. And that makes sense. If it's going a lot faster at the equilibrium position, that means it's now, it was going boing, 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 boing. You eject out and it boing, 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 boing. Okay. Got through? Okay. Well, it's 8 o'clock. The exam, I think, is a fair one. There are 25 questions, 4 points each. And I think if you feel comfortable with those sample exams, you're ready. Okay, this exam historically has had high averages. So good luck. You're welcome.
So bad. Yeah, it's my future.